Hi again. So in order to demonstrate triggering for analyzing analog signals, I'm going to create a circuit for you and actually go through the whole process setting up the triggers, and then we can see how we analyze a RC network. So the circuit I've got here is a 5-volt DC supply, and we've got a switch here which allows us to connect the 5 volts to my circuit here, and similarly I've got another switch here which allows me to discharge this circuit equally, and if I want to get rid of the voltage charge across my capacitor here, I can press SW3 briefly just to discharge this, so I know I've got 0 volts across here. Now, I don't know how many of you know about RC networks, but the general theory is that one time constant equals RC. So that suggests that if R is in ohms and C is in farads, and what it says is that the time to get to 63% of the voltage going in can be given by RC, i.e. 10K and 10 microfarads. So that means that we've got T is equal to 10,000 times 10 microfarads, but remember this is in farads, so it's 0.000010 farads, and that equals 0.1 of a second. So this means that if this voltage across here is 0, because we've reset the capacitor and we've made sure there is no voltage across here, and then I press SW1 and keep it pressed, then the voltage here is applied to this circuit, and the voltage then will charge up this capacitor through this time constant, and this voltage here will get to 63% of 5 volts, which is 3.15 volts, in approximately 0.1 seconds. So that's on the basis that the tolerance of these is accurate, i.e. This is actually a 1% resistor, but capacitors are notoriously variable, in that could be plus or minus 20%, possibly even more. But we'll have a look and see what happens when we analyze the circuit. Similarly, if this capacitor is actually fully charged and it's got 5 volts across it, then what I can do is if I press just SW2, then I can discharge this circuit, and this suggests that in 0.1 of a second, if this was 5 volts, then when it would reach approximately 1.85 volts after 0.1 of a second. So what we're going to do is see how we set up an oscilloscope to actually capture all of this and analyze all of this. So what I've done is we have a circuit here, and here, let me just get my pointer here. So this is SW1, which is my charging switch. This is SW2, which is my discharging switch. This is my reset switch, which discharges this capacitor here. And this is my charging resistor, discharge charge resistor, 10K value here. So I've got channel A of my oscilloscope connected to across the capacitor effectively, so I can look at what's happening across the capacitor. And similarly, I've got channel 2 connected to the actual resistor, so that I can look at triggering in a little bit more detail from a different perspective. But we're going to look at it first from a channel 1 perspective. So let's see how we get on. So let's go back to our screen, and what I'm now going to do is the PicoScope I've started up. So this is from its reset condition. This is on power up because I wanted you to see and understand the process by which I'm going to be looking at this circuit. So first of all, what I can say about this is we've got 5 volt signal here. So we're going to first look at the amplitude of the signals we're dealing with. So none of these signals are going to be anything outside 5 volts. So they're going from 0 to 5 volts. So the first thing, and also I don't want my scope leads having any effect on this circuit. So I'm going to make sure my scope leads are on times 10 to maximize the impedance, so this has minimum effect on my circuit. Okay, so let's have a look at how we set this up first. So let's go to channel A, and we're going to go to the probes, and we're going to go to times 10 on that probe. And similarly, I'm going to go to channel B, probes, and I'm going to go to times 10 on there as well. We also know that the signal on here is going to be, if we want to catch 5 volts, I'm going to make sure this is actually plus or minus 10 volts, which is absolutely fine, which is default. And I'm similarly going to do plus or minus 10 volts on here as well, and make sure that's okay. So we've got both signals on. I'm going to turn channel B off for the time being. And we're now going to look at our signal and see what happens. Now then, from a time-based perspective, we know that let's go back to the presentation. We're looking for 0.1 of a second here as a time constant. Remember, that's one time constant. So what we're going to do is set up our time base for 200 milliseconds per division. Yeah. And let's have a look at our triggering now. So on the triggering, we are going to trigger on channel A. We're going to, just a simple edge is what we're looking at. That's all we've been discussing in this. We're going to set our pre-trigger to this center point here, and we're going to set our threshold to half the voltage. For example, 2.5 volts, because we know we've got a 5-volt signal. So let me just enter that to 2.5, and now you'll see the trigger has been set here. Now you'll notice you're in auto mode, so this is scanning. If it can't find a signal, it'll carry on scanning and finish the signal. Now what I'm going to do now is I'm going to change this to single shot, because all I want to do is see one event and just capture that event, and then I don't want to worry about the triggering anymore. So I'm going to go to single shot. And single shot is now waiting. Remember, it's running here and it's waiting for an event to occur. So what I'm now going to do is I'm going to go back to my circuit here, and I'm going to make sure my capacitor is discharged by pressing the discharge switch here. And then when I'm going to trigger my circuit, I'm going to press this switch here, and that is going to, I'm going to press it and hold it in, and that's going to charge up, put the voltage into my circuit so I can watch the charging phase of the capacitor. So let's just go back to our screen. So let's just make sure we're ready. So we're armed and ready because we're running here. We're looking at channel A. We're looking for a 2.5 volt threshold, a rising edge. And now I'm going to press my SW1, which is actually now going to apply power to my circuit. I'm going to keep my finger on that switch, okay? So I'm going to press it now, and there we go. And I'm going to release my switch now, and you'll notice this has stopped. So I've now captured the rising event here. This is the typical charging characteristics of a capacitor from a switched source, and as you see, it's terminating at 5 volts because I kept my finger on the switch, and I can look at this ramp time here. Now what's really interesting is, let's have a look at the time constant on this. So I said to you that for one time constant we're looking for 3.15 volts, so we can actually use the threshold to actually analyze this circuit. So I could change this threshold here to 3.15 volts, and now you'll see it's changed here. So let's have a look and see how accurate our components are. So I'm actually going to discharge my capacitor. Let me just show you what I'm doing here so you can see this. So I'm going to discharge my capacitor by pressing this switch here, and it only needs to be touched for a little while, and that now shorts the capacitor out, so it gets rid of any voltage that was on the capacitor. And then when I press this switch again, I'm ready to look at a rising edge and see my charging characteristics. So I'm now going back to my screen. Now remember, this is stopped, so I can examine this in detail. I'm going to rearm this, and now you'll see it's waiting for an event to occur. I'm now going to press my SW1 and keep it held in, and there we go. And I'm now going to release SW1, and now at my leisure I can look at this in detail. So let's go back to here, and what it says is that for 63% is one time constant, it should be 0.1 of a second. Well, let's have a look and see what we've got on our circuit. And this actually is a really good demonstration, because now, because we set our threshold to 3.15, which is 63% of 5 volts, then because we set our trigger to that point, then I can look backwards in time here, and I can look at what is the time here. And that actually, interesting enough, is actually not far off 0.1 of a second, which is pretty amazing. So it goes to demonstrate that the capacitor here and the resistor are actually quite accurate. I know the 10K is pretty accurate because it's a 1% resistor, but I don't know much about the 10 microfarads, and that suggests it's actually not far off. So this is a really good example of capturing circuits. Now, similarly, I could actually capture the discharge. So let me just go back into my PicoScope, and what I'm going to do now is I'm going to change the edge to a falling edge. And to get the discharge characteristics, I'm going to now set the threshold here to 1.85 volts, like that. So it's good. And now I'm going to make sure that my capacitor is fully charged, because I'm looking at a discharge characteristic here. So I'm going to press, let me just show you what I'm doing here. I'm going to press SW1 to charge my capacitor to make sure it's fully charged. And then I'm going to press SW2 to actually discharge it. And the reason I'm charging it first is that the oscilloscope has a loading effect on this, and it would be slowly discharging this capacitor through the actual resistance of the input impedance of the scope. So I just want to make sure that's as charged up as possible by keeping SW1 on before I then press SW2. So let me just go back to my circuit here, and I'm just going to press SW1 to make sure my capacitor is fully charged up. And then I'm going to run my trigger circuit. So you can see this is sitting at 5 volts. And now what I'm going to do is release SW1 and press SW2. And now you can see the discharge characteristics. And once again, because I've set the threshold at 1.83, which is 63%, from a falling perspective, going from 5 down to 0. And I can look at the time here, the time constant, and equally, it's around about 100 milliseconds, which is 0.1 of a second, which is what we calculated in our calculations here for T is equal to RC. So why have I got the scope, the channel B connected here? Now, I'm using the threshold here to catch the signal just on channel A. But what I could do is actually trigger on channel B instead. So I'm going to switch on channel B, and we are going to go to manual, and we're on plus or minus 10 here, which is great. All these conditions are correct. And I'm now going back to the triggering waveform, and I'm now going to trigger on channel B. So it's triggering on channel B. And I know that channel B, if we go back to our circuit, channel B is fundamentally either going to switch to 5 volts or to 0 volts, depending on what I do with SW1 and SW2. So what I can now do is I can set the threshold here to be 2.5 volts. And now you'll see that trigger point there. What I'm going to do is separate out these waveforms so it's a bit clearer. So I'm going to raise this waveform up to, that's the channel A up, and I'm going to bring channel B down here so it's a little bit clearer about what's going on. Now remember, I'm running and I'm on single shot. So what I'm going to do is I'm now going to discharge my capacitor. So I'm discharging my capacitor by pressing SW3 here. So that makes sure there's nothing on there at all. And then what I'm going to do is switch SW1 in to charge the circuit. But now I'm using the channel B, which is a square waveform edge. So it's going immediately from 0 to 5 volts. So it acts as a very positive trigger. So let me have a look at that. And so we're going to rising edge on channel B, and let me just now press SW1 and see what we capture. And there we go. So now here is my trigger event, which is a rising edge. So if I go back to the circuit, this is because all of a sudden I've switched SW1 on. I've got a sudden rising edge here, and that makes a very positive trigger event from my scope. So I'm triggering from channel B, but now I can clearly see what's going on with my channel A. So I'm using two sources. One is to look at my signal, but the other one is actually to trigger the actual event in the first place. And this has got a very positive characteristic. It's as soon as I switch the switch, and now I can see my charging circuit charging up. And so this hopefully demonstrates how, one, you can use the threshold to actually analyze circuits, but equally you can actually capture an event through a different channel. So you can use different sources to actually view a synchronized event. And this is what I'm trying to demonstrate here.